All right, welcome back, everyone. In this lecture, what we're going to talk about is water, and both getting it into the house or building or structure with plumbing, and also getting it out of the house with drainage. So this corresponds to book chapters number 15 and 22. So a bit of a combination, much heavier on chapter 15 than 22. So what we're going to talk about are codes, laws, industry standards, water supply, bringing the water in, building water supply, design considerations, what are we going to do when we're designing our systems, also sewage and stormwater differences in those and how we deal with those systems as well. Sustainability for water, as we start off every section with sustainability. Of course, conservation is a big one, conserving water. Comes into play when you talk about water fixtures. You might have heard about shower heads where they decrease the flow rate and people complain it didn't get the shampoo out, right? But conserving water with the fixtures. Toilets, we've definitely moved to low flow toilets. That's been a big deal over the last 20 years or so, maybe 30 years. You ever see an old toilet and they flush it, you know they use a ton of water, right? Within the building, if we talk about sustainability, the International Building Code requires these water conserving devices and fixtures, like I said. Within the water supply to the building, there are some instances where you can actually recycle rainwater or stormwater or gray water, right? So there are opportunities to recycle this water. Gray water is water that's coming out of the house that doesn't have the solid particulates. So codes, laws, and standards, where do they come from? Of course, water safety is heavily influenced by the codes, public health and safety. There's the International Plumbing Code, sets up the individual requirements. EPA standards for what the drinking water should look like. As water is treated, we're adding things, some things to it. We're taking out other things. How are we doing this? What are we doing, and what should our water look and taste and smell like, right? Sanitary, sewage and stormwater dictated by local jurisdiction. So like City of Fort Collins might have a different way that they're managing their stormwater and sewage than something like Vail, right? So let's move on to water supply systems, getting the water to the building. So of course, the big thing is we need to get the water from the source, which could be like a reservoir or something, right? Treat it, make it drinkable, and then supply it to the building. Now, when we talk about distribution to the building site, away from the building, that'd be chapter 22. Within the building, that's chapter 15. So starting with 22, how do we get it from the point source to the house? Well, we're originating at something like a lake or stream or some underground sources. Do you know where your water is coming from in Fort Collins? Horsetooth Reservoir has a big piece of it, right? We're storing our water. How do we get it from Horsetooth Reservoir to our house, and how do we treat it and get it purified? Water main, supply it for individual buildings and users. We treat it for safeness, and we can soften it. Softening the water is removing some of the calcium, iron, and other minerals that are not very conducive to taste or for the system in general. We also want to reduce the corrosiveness. Same idea. We don't want the water to have any minerals that will affect the corrosive properties of plumbing within the structures or the distribution system. So moving on to, once the water is at the structure in the building, we need then to distribute the water within the building, right? What are some goals? We want to keep that water from becoming contaminated, because that's the way our city has supplied us with the water. We don't want to introduce any new contaminants. Maintain adequate pressure and flow for the particular plumbing fixtures and appliances. So we need the pressure to be there. We'll talk more about that in just a little bit. Prevent excessive flow and consequent waste of valuable water. Too much flow is actually bad. You can have too much pressure. Prevent excessive pressure, like I was just saying, velocities, corrosion, and scale buildup. Provide water without any noise, fixture staining, or odor. So once the water is within the building, there's really two different lines or branches that we're concerned with. One is the hot water The other is the cold water. Do we need the water to be hot or cold? And we consider these to be trees. The hot water tree, of course, has to have a hot water heater within that system so that that whole tree is hot, versus cold water can be directly from your city line, right? When we talk about these trees, there are risers and branches. Risers are the vertical part that's coming up through our structure, versus branches are our horizontal runs. And as an alternative, what we can use with all these different branches is an idea of a manifold. Now, here's a diagram of a manifold down here with PEX piping, and we can see blue represents the cold branches and the red represents hot branches. At least that's what I would assume. Now, this is a little different because what I have is each individual branch is going directly to that fixture, as opposed to having branches and then continuing on to a separate fixture. There's advantages and disadvantages to both. In general, we can talk about upfeed or downfeed water systems. What an upfeed is, and these are based on the height of the building and what required pressure I need. Generally, we think of upfeed systems for residential. What that means is we're relying on that pressure from the city to distribute the water throughout the structure, right? Simpler, less expensive. However, it's limited because, as you may know, as I have pressure going up in height, the pressure is actually used to bring that water up to that height, which means that we're losing some of our liquid head. We're losing some of that pressure that is available to us as we move higher in our system. So with these upfeed systems, we do have a limit of like 40 feet to 60 feet. Once I get to some taller structures, I need to use a different system called a downfeed system, where I put a storage tank somewhere up high, probably on top of the building, and then let gravity actually increase the pressure to feed these fixtures, right? And of course, we can have a combination of systems like this picture here, where in this case, I have a pump pumping it up to this tank, and that tank is feeding downfeed to our fixtures down below. But I could also, on the very bottom line, I see I'm just upfeeding to those fixtures. I have another separate tank here to downfeed to those fixtures. So downfeed just means that I'm increasing pressure due to the location of the water, versus upfeed, I'm losing pressure due to the placement of the water, the fixtures. When we talk about designing these systems for an upfeed, I need to determine what that pressure is coming in from the main line. If it's residential, it's probably somewhere between 40 and 60 psi. Could be higher, and I may have to actually use a pressure regulator because I could have too much pressure like we talked about before. Once I have that incoming pressure, then I can subtract what is that highest fixture. That's called the static head. How much higher? And it's a direct relationship to pressure in height, right? So subtract that pressure that I have for the height, subtract the pressure based on the fixtures. What's my requirement for the shower head and toilet up on my upper levels? And to add up all those and subtract it from how much I have coming in from that incoming pressure. I'll also have loss of pressure due to friction in the system. So from these pipes, what are the size of the pipes? What's the material made out of? That dictates the resistance that I have, which means I lose even more pressure. What kind of fittings do I have? I lose some pressure at the meter as well. So I have to look at all of these losses, see what I have coming in, and make sure I still have enough excess pressure to supply what I needed. So that's basically the way the system is designed. There's a lot of calculations involved to size the system, is what they call it. Meaning what size pipes, what pressure is needed, can I use an upfeed system, things like that, right? For the downfeed, it's the exact same thing. We still have all these losses. The only difference is we subtracted the pressure to raise it to the highest fixture. We call that static head. Well, in downfeed, we're actually increasing, we're adding pressure due to that static head. So that's the only real difference between upfeed and downfeed for calculating the size of the system. And another design consideration, more of an efficiency type thing, rooms with plumbing fixtures should be located near to point of entry to the building as possible, of exit to sewer line, and the point of exit to the sewer line should be as close as possible, and possibly even clustered together. So the idea behind this is we want to minimize the lines, just because, like I said, we have friction involved. If we have longer lines, we have more joints involved. So it's more like designing a system so that it will be more efficient, right? Either it be a manifold type system that we were looking at earlier, or having something where your number of branches are minimized, or you can use multiple fixtures off a single branch. So more design considerations. Walls used for vertical distribution are called either wet walls or chase walls or plumbing walls. And sometimes you'll see these chases or something else where you have a wall that's suddenly thicker than the other walls in your house. Instead of 2x4 walls, they become 2x6s. That's to accommodate your plumbing, especially like your vent, which we'll talk about a little bit more in waistlines. But any kind of plumbing, we need room for that inside those walls. Wet walls, chase walls, plumbing walls. Also consider ease of access for future maintenance. As someone who had to go into an old 1950s house and replace all the galvanized plumbing with copper plumbing, I had to break through a lot of walls when I couldn't access it from either the attic or the crawl space. So definitely I am a big believer in having room to be able to access all these plumbings. You may want to add fixtures or add a line, or you may have a leak or something you have to have maintenance for. So like I said, I had to replace a galvanized pipe with copper. You don't see galvanized as much anymore, but when we talk about water pipe materials, what's going to be used for these water lines? Of course, the plumbing codes will dictate a lot of this, and we'll need to look at things like the air and the acidity and the carbon dioxide and the mineral contents of the materials that are carrying our water, right? So galvanized steel, like I said, not used as much anymore. Still low cost, high strength, resistance to high pressures. It's a thicker walled tubing, so it's very strong, right? However, they have these threaded joints, so it's very labor intensive to piece together a galvanized plumbing system. You have to plan ahead and screw everything in. You might have, this is called a union here, so I can't actually turn the pipes individually, but typically if I were building this out from this T, and then I have this nipple, and then I have a 90-degree elbow, and then I have another nipple, and then I have a union, all those pieces need to be threaded if they aren't the right length, otherwise sealed with a pipe sealant. I can see that tape, it looks like right here, or you could put a gunk on there. So that's our threaded joints. It leads to a lot of labor-intensive work, right? Steel tends to scale and corrode, which can reduce pipe diameter. That is why I had to replace a lot of my galvanized steel plumbing, is because if you were to cut into one of these pipes after years of service, what you see is your pipe started out with a large diameter for water to flow through, and then you have all this corrosion and you end up with this tiny little hole. So when you turn on your water in your sink, you're just getting a little flow of water. Where'd all your water go? It's restricted by these pipes, right? Also, when you first turn it on, they may be kind of brown, reddish, right, as you're flushing out some of this corrosion on these pipes before it runs clear. Really kind of nastier stuff, and that's why galvanized isn't really used so much anymore. Very hard water and very hard water should both be treated. Okay, fine. Very hard water should be treated. Don't know why that's in there twice. I think a typo. Should not be laid in concrete, yeah, because there can be a chemical reaction between the concrete and the galvanized, and it'll erode away. So the water can erode it, and concrete can erode it. Galvanized steel, fun stuff. Instead, one of the big transition from galvanized moved over to copper. Copper is more expensive, especially lately. The cost of copper has gone up. However, it is easy to join, and it is also corrosion resistant. So when we talk about joining copper, we talk about sweating pipes. If you've ever done this, you put on this flux, which is this almost like a primer material around our pipe. Then we put our pieces of pipe together. Then we have like a blowtorch on one end, and we have our solder on the other, and it sucks the solder right into the joint, makes it totally waterproof, right? Kind of a cool process. Another way is with these new things called shark bites, where you're basically just pushing your pipes together, and the connection is like a one-way joint type of thing, right? But either way, they're much easier and quicker to join than having everything threaded. I can cut them to whatever length I need. I don't need to have a pipe threader on site in order to thread all my individual pieces. You should not have a high carbon dioxide content. It'll turn your copper green, not good stuff. Should not be used for higher velocity systems because they're relatively weaker joints. Yeah, you do not have the strength that you would in some of your other metals. Rigid pipe or flexible tubing. I can see I have some flexible tubing for a smaller diameter, lower flow type of pipe. Could also have plastic piping. Some plastic pipes are not suitable for carrying drinking water. We are seeing more and more of it like this. This is like a PEX, which is a name brand plastic made out of polyethylene, and I can see it's color coded, either red for hot, blue for cold, threaded around here. Anyways, it's lightweight, better insulator. Joints are permanent, yeah, mainly, yeah. Large coefficients of thermal expansion can cause length differences with changing temperature. So if you think about hot water, plastic, plastic generally expands more than like copper or galvanized when it's heated. So you could have some issues if you had a really long run with expansion. Low strength requires support, generally made out of PVC, chlorinated PVC, or polyethylene. Simpler and less expensive than some of the other systems. I think that's why I'm seeing more and more of it. And like I said, they're more likely to use that manifold system as opposed to the branches in the trees. This is actually a waste system. We talked about PVC before, so this is a PVC waste system with a vent coming up. We'll talk about that in just a little bit. Plastic definitely in this side as well. To control the flow of water, we use these things called valves. The different types of valves. We could have a gate valve, and I can see the way a gate valve works is there's this wedge that can raise and lower based on this handle up here. As I turn this guy, it would raise that gate, and if I lower the gate, then of course it decreases the flow. Used for full unobstructed flow when open, zero flow when closed. We have globe. The way a globe valve works is I have these two chambers. So I have, in this case, I have it closed. So I have this water chamber and this air chamber separated by this plunger. So if I pull this plunger up, then water can flow through from one chamber to the other and then out. So this is a globe valve. Last is called a ball valve or an alignment valve. I have this single lever and I have this ball with two big holes in it, and you can see how it would be closed the way it's shown here. And as I turn the handle and align, hence the alignment part, these holes with the pipe, it allows water to flow. There are no washers. There are washers in both these other systems, but this has no washers, less likely to leak. And you can see it's a quicker operation because I just have the single handle and I'm turning it 90 degrees. So that was bringing water into your building. Let's talk about getting it out. Sewage versus drainage. Building drainage, sub-drainage systems, and storm drainage. What is the difference between sewage and storm water? Either way, we're getting water away from our structure. The question is, did it originate from inside the structure or did it originate from outside the structure? Meaning I can see here if I had some rain or some snow hitting this, going down this gutter, coming down, and now I'm in this storm water side of things, right? Versus on the other side, I have this sanitary sewer, which is coming from our sinks and our toilets and everything else inside the house, right? Now, in general, I want to keep these two separate from each other, although some codes did allow you to intermingle them, right? What about this whole sanitary sewage? These are sewers that are underground, conduits, and carry off liquid or solid waste. We have the building drainage system, a drain waste vent, or a DWV system, right? That's inside the building. Begins from a point 3 foot outside the building and then includes everything that's going on inside the building. Versus a building sanitary sewer, which is starting from that 3 foot away and then going to that public sewer line. So looking on here, what we're saying is we're still talking about inside the house. So now we're talking about that one that comes about right here, goes into the sanitary sewer, right? And this is what I was saying before. Sometimes you might be able to get away with combining your sewer system and your building drainage system and your building sanitary system, but It can be easily contaminated, more frequently being banned. It puts a higher stress on the water filtration system too of the city, because you're taking this water and you're treating it in different ways based on where it's coming from. So this DWV, this is inside the house, right? This is our drain, waste, vent system. First thing to note is you need to have the right slope for all of your piping to get the water out of your system, right? Because this whole thing is called a gravity system. There's no pressure that is pushing the water out of the building. Instead, it is just the gravity feed. So it's just the slope and gravity pulling. And if you had zero slope, then everything would just sit there in the pipes. It could lead to leaks, and it's just not good for the overall system. If you have too much of a slope, what happens is the water runs out too quickly, leaving away these solid particles. So it could be waste from the sink or from the toilet, even grosser, right? So instead we want the correct slope, 1/4 inch to 1/2 inch per foot. That way we have both liquids and solids draining through this system due to gravity. The components of a DWV system, we have the D, which is the drains, carries building sewage via a system of pipes like we were just talking about. We have traps. What a trap is like you'll see this anytime you look underneath a sink. You'll have this little U shape, right? The purpose of that U shape is as water comes down, you can imagine it fills up, and then the water would overflow and go down into the rest of the sewer system. But what we don't want is the sewer gas coming up from the sewer, from that line, coming into our house. So what this little trap does is it traps the air, the sewer gas, from coming in and getting into our house, because it'd be stinky and nasty and could be even harmful, right? We have vents. We have a vent, provides the flow of air to prevent siphonage of traps. This is my pipe vent. So anytime I have, after a trap, if I'm going down into a vertical run, you can imagine that gravity would be pulling this water down. If I didn't have this trap, if this were just closed right here, then it would just suck out all of the water out of the trap, and I could have all that sewer gas coming into the house. So instead, we vent it so it has, so it doesn't get that suction, right? And this venting will be usually combined into a couple different, and then going up to the roof of the house. So if you ever work on a roof of a house and see some pipes sticking out, go over there and take a big whiff, and you'll get some sewer gas. Pretty nasty stuff, but knock yourself out if you want to try that. Storm drainage. So we said storm drainage is different than this DWV, because storm drainage is that rainwater, surface water, condensation, cooling water, all this stuff outside of the building. It's that type of drainage, right? So we could have different ways to get it away from our building. We had under slab drains and footing drains. We could have storm water collection devices like gutters and downspouts and overflow pans. So here I see a sub-drainage system. Sub-drainage meaning below the ground. This one's a foundation drain. Foundation drain, you can see it's this pipe right here. Collects and carries off groundwater and stormwater that may seep down. So either groundwater that's coming up, or if I have some filtration from rain or anything else, right? And you can almost see how it would work. We're putting this drainage fill, which is a material which allows the water to flow real easily. So water would naturally want to flow, path of least resistance, through here, hit the foundation drain. Foundation drain typically has a bunch of holes in it. Water goes into the hole, and then it runs out into the drainage system. Of course, codes may require that you have to have these depending on your water in that area or how they're dealing with the water. Foundation drains are placed at the bed of compacted drainage fill material around the exterior perimeter of building's foundation. Like I said, that perimeter, that fill allows water to run easily through it. Foundation drains are frequently used in conjunction with waterproofing. Yeah, so you waterproof your building, direct the water someplace, it has to go somewhere, right? So you put it into one of these foundation drains. You could also have under slab drains, almost the same thing, but instead of being next to your foundation, it is under a slab. Same idea, you still have this fill material, so if water were to get under your slab, it would want to flow along here, path of least resistance, go down here, collect until it can get into this drain, and then whisked away. So that's what I have for this one. Hope you like the rest, found it informative, and we'll talk to you all later. Thanks.